Okay. Okay, ladies and gentlemen, we're continuing with chapter 6 now in the textbook of Sengel and Gajar. We've done now, or in the previous course, you've already done the 3 different types of heat transfer: conduction, convection, and radiation. We did transient heat conduction or unsteady heat conduction, and we also did go back in fluid mechanics to look at the derivation of some of the differential equations, which are very important to us. Now, the next few chapters are all about convection, and that is really the difficult part of heat transfer. So the convection part consists firstly out of a chapter 6 on the fundamentals of convection, and then after that there will be 3 more chapters. The one on external convection, another one on internal convection, and another one on natural convection. Okay, so this chapter is very important as a foundation chapter for the following 3 chapters that's going to follow. Now, the chapter has a lot of material in, but many of it we've already covered, either in the chapter of White or in your other fluid mechanics course. So on some of it we're going to go over very quickly, just on the surface, just to do a little bit of a revision. But you will see this chapter consists firstly of the mechanism of convection, then the classifications of fluid flow, the velocity boundary layer that you already did. Then we're going to introduce the thermal boundary layer. Then we're going to look at laminar and turbulent flows, heat and momentum transfer in turbulent flow, then the derivation of the differential convection equations, we already did that. Then the solution of convective equations for a flat plate, and then non-dimensionalized convection equations and similarity. Then part 10, functional forms on friction and convection, and then lastly 6.11, analogies between momentum and heat transfer. So it's quite a long chapter, and if everything goes well, we're going to cover it in about 3 lectures. Okay, so let's start with the fundamentals of convection, and just look quickly again at conduction, convection, and radiation. Conduction, convection, and radiation. For each one of them, you already did the necessary equations. Now, to explain convection, let's just go back quickly to conduction, and let's look at the differences of the 3 different modes of heat transfer. The one thing that is different from conduction and convection is that it needs the presence of an internal or material medium. Okay, so there should be a presence of a material, and the material can be, in the case of conduction, can be a solid, or it can be a liquid or a gas. And I'm going to show it to you just now. Radiation is different because it doesn't need a medium. Okay, it doesn't need a medium, it can radiate right through a vacuum. So that is what is different from a radiation heat transfer. Now, if we just come back to conduction again, and the mechanism of conduction. With conduction, if we've looked at a body, then we've said that typically in a solid, there will be molecules, and they are relatively close to each other. And as we know, they vibrate. Okay, and because, especially in something like copper or diamond, they are very, very close to each other. If we now increase the temperature here, we give this molecule more energy, and it will bump against the molecule next to it. It will become more excited, it will start moving faster and faster, and that is the mechanism of conduction heat transfer. So normally we've got this structure of a densely packed material, and that is now a solid. Now let's start making the molecules moving further and further apart. Okay, and there are solids like that, and that would be solids which do not have a high thermal conductivity, but in the limit, we can also start moving over to a gas or to a liquid. And the only difference is going to be that the distance between the molecules is just going to move further and further apart. Okay, so the question is now, well, if it is a gas and I heat that molecule, is the heat transfer through the medium by conduction, or what is this thing of convection now coming in? What makes it different? Okay, now the difference between the two is that with convection is always in the presence of bulk fluid motion. Okay. So bulk fluid motion. What do we mean with bulk fluid motion? It means that most of that fluid is actually moving. Okay, it is moving. With conduction, it will be where there will be an absence of a bulk fluid motion. And that is one of the most important differences between conduction heat transfer and convection heat transfer. And let me illustrate it to you with a very simple example. Let's look at the case where we have a flat plate, okay, which is at a temperature of 50 degrees Celsius. Okay? And we have a fan which is forcing air at 20 degrees Celsius and a velocity of 3 meters per second over this flat plate. Okay, so what happens with this medium here? We have a bulk fluid motion. So all the fluid would sort of move over the flat plate. Okay. And this flat plate, if it meets a beautiful molecule here, it will see it once and then it's gone. Okay, so it's going to disappear, okay, in general. So, and that would be forced convection. Okay, so we call that forced convection heat transfer. Forced convection, remember HT, just heat transfer, forced convection heat transfer. So this heat transfer rate, let's call it Q.1. That is forced convection heat transfer. Now, let's suppose there's no electricity, okay, and the fan stops working. Okay. What is going to happen? Now it's the same plate. It is at 50 degrees Celsius, okay? And now we know the air here is going to be at 20 degrees Celsius. Its velocity is going to be 0, but because this hot plate of 50 degrees Celsius is going to heat that molecule there, okay, or the molecules in that region, its density is going to decrease, and the result is that the buoyancy force is going to move it up. So we will start creating very, very low velocities very, very close to the wall. Okay. And that is also what is happening now here in this venue. If you sit here, your skin temperature close to maybe 37 degrees Celsius. This venue 23, well not 24, 25 degrees Celsius, and it would heat the air, and the heat close to you would rise up, and it would cause some currents that starts flowing into this venue. They are not, the velocities are not that high that your air is going to stand up like that. Okay, so we call that natural convection. Okay, so the bulk motion, the fluid, it moves, okay? And therefore, it is called natural convection. Now let's suppose, okay, and what is very important here to remember is and we didn't put it in, is that gravity is working in this direction. Now, let's suppose we do the same experiment with air, again at 20 degrees Celsius. Okay. And the plate still at 50 degrees Celsius. So in all three cases, the plate temperature is 50 degrees Celsius, but different environmental conditions. But now, the gravity is equal to 0. Okay, so there's no gravity. Okay. So, that molecule is going to be heated. Okay, now what is it going to do? It is going to be excited, and it is going to bump against another one, and the mechanism now is conduction heat transfer. Okay. So in the limit now, we have here conduction heat transfer. And it doesn't matter if it is a gas or a liquid. We can have conduction heat transfer in a gas or a liquid also, okay, in the limit. Okay, now in general, we know that the higher the flow or the bulk fluid motion is over a plate or whatever, the higher the heat transfer rate will be. Okay. Now, the study of convection heat transfer is quite a difficult subject, a difficult field. It is still open for a Nobel Prize, and I'm going to show you just now why. Okay, and so in the study of this, obviously engineers looked at this and say, you know, how are we going to solve this problem? And from many experiments, what I have found, so from experience and experiments, if you start doing experiments on it, it has been found that the convection heat transfer rate, is a function of quite a number of variables. If we look now at this case of the flat plate, it would be a function of, okay, I'm going to write it here, it's going to be a function of the viscosity, the K, the rho, and the Cp of the fluid. Okay, which means it is the fluid properties. Okay. So from experiments, we know that if we do this experiment with water, with air, then we get different results. If the air is at a temperature of 20 degrees Celsius, in comparison with 20 degrees Celsius or 400 degrees Celsius, it's going to influence these variables, and because of that, the heat transfer rates are going to be different. Okay, so it has been found from experiments. Then also, we know that the velocity is a very important variable, the free stream velocity, and obviously the surface temperature and the free stream temperatures are also important. But now there are other variables which are also important. If we do this experiment for a flat plate, and then I repeat the experiment for a cylinder or a sphere or an aerofoil, then the results change. So it is also a function of geometry, the geometry of the body, okay, and surface roughness, and also the flow regime. So is the flow over the body in the laminar flow regime? Is it in the transition flow regime? Or is it in the turbulent flow regime? Okay. So this very, very complicated relationship of the heat transfer rate as a function of all these variables, Newton really took a shortcut with this. Okay, and what he did is he said, well, let's make it very simple. We know that if things are simple, then usually it works easier and it's easier to understand. So he said, well, all we do is we are going to say the convection heat transfer is equal to the heat transfer coefficient multiplied by the surface area multiplied by Ts minus T environment. Okay? Or you can write it as the heat flux of convection divided by the area is equal to the heat transfer coefficient multiplied by Ts minus the free stream temperature. Okay. Where this guy here, okay, the heat transfer coefficient is now a function of all these things that we've discussed on this side, except now surface temperature and the free stream temperature. Okay. So he made it very, very simple. So where's the Nobel Prize? Well, the Nobel Prize is if you can derive from first principles what the heat transfer coefficient will be, always as a function of that, then I'm sure you'll get it. Okay. So that is the challenge. Hasn't been done yet. So if you can get that very, very simple relationship, and in nature things are simple, so it will be a simple equation. That we also know. It will be a simple equation. Right. So we know that this H is called the heat transfer coefficient. Okay, the heat transfer coefficient. In many cases we are going to write out HTC, the heat transfer coefficient, and its units is watts per square meter degree Celsius. Okay. In many cases, people are confused because sometimes they see it as watts per square meter Kelvin. It's the same, it doesn't matter, because in this equation, if you work with Kelvin or with degrees Celsius, doesn't matter, it's the same delta T, and you can write the convection heat transfer coefficient as per degree Celsius or per Kelvin, it doesn't matter. Okay. Right, now this heat transfer coefficient has a definition. Okay. And the definition is quite long, and I'm going to write it down as 4 important steps. And this definition says it is actually the rate of heat transfer. Okay, I'm writing it out now, it's very simple. The rate of heat transfer, okay, between a solid and a fluid. Obviously the fluid can also be a gas. Per unit surface, per unit surface area, and per unit temperature difference. So that is actually the definition of the convection heat transfer coefficient. Okay, now let's look at our fluid mechanics, and that is why it is important, why we cannot really separate heat transfer from fluid mechanics. You've already done it with boundary layer theory, that if that is the free stream velocity, okay, that if there's a solid surface, then there will be a boundary layer developing like that. Okay. And far away from the surface, that velocity would be equal to the free stream velocity. Okay. So if I would now keep my measuring instrument there, and I would bring it closer and closer and closer up to the point where that velocity is equal to 99% of the free stream velocity, then you have learned that that is the boundary layer thickness. Okay, boundary layer thickness. And that is being caused by viscosity. And also the fact that the velocity there must be 0, and that is also called the zero slip velocity. So the velocity is there is equal to 0, there it must be equal to the free stream, and in between there's a differentiation in terms of velocities, and when we measure the velocity where that velocity is 99% of that one, then that is the height of the boundary layer thickness. Okay. Now, what is this implication of the non-slip velocity? That is quite important for us from a heat transfer point of view. Because if we now try to think of the heat transfer, what is the mechanism that occurs here, then it is actually, how is the heat being transferred? Because what we say now is that the velocity there is equal to 0. Okay. So it means that on the boundary, the heat transfer mechanism is by conduction. Okay. So let's look at it in terms of the implications. Okay. So the implications is that the heat transfer from the solid surface, okay, so the heat transfer from the solid surface to the fluid. The heat transfer from the solid surface to the fluid. Let's look at the convection. The convection must be equal to the conduction. And the conduction is equal to minus K, take note of the fluid, okay, multiplied by partial dt dy, where y is equal to 0. So it is that gradient there. Partial dt dy, where y is equal to 0, and we choose that as our y-axis. So where y is equal to 0, that gradient there, that would be the conduction heat transfer. Now from this, let's call that equation 1, okay, equation of convection heat transfer. Convection flux is equal to the heat transfer coefficient multiplied by Ts minus T infinite, and this one equation 2. So let's equate equations 1 and 2, and then we get that the heat transfer coefficient multiplied by Ts minus the free stream temperature is equal to minus thermal conductivity of the fluid multiplied by partial dt dy, where y is equal to 0. And the result of that is that the heat transfer coefficient fundamentally is equal to minus the K value of the fluid multiplied by partial dt dy, where y is equal to 0, divided by Ts minus T infinite. Okay. So, what do we say? We say that at the wall, the mechanism of the heat transfer is by conduction. Okay. Once the conduction occurred, obviously from there on it is convection. But because of this, we can actually write that the conduction must be equal to the convection, and the result is fundamentally that the heat transfer coefficient can be determined if we have the temperature gradient very close to the wall. Okay. So if you can go and measure the temperature gradient very close to a wall, then you can get the heat transfer coefficient. However, it's almost impossible to do it. You have to do, there are experiments in which it can be done, but they have to be controlled very, very carefully, and in general, for most practical bodies or things that we want to calculate the heat transfer from, and before we can do that, we need the heat transfer coefficient. It is not possible for us to go and measure it. Okay, so we need to make another plan. Okay. Now, in general, what is also important to realize is that the heat transfer coefficient is not a constant. It is actually something that is a function of position. Again, let's look at the flat plate case. Okay. So if we look at the flat plate, and that is the free stream temperature and velocity, and we look now at different positions, 1, 2, 3, and 4. Okay. And let's suppose you can go and do those measurements. Okay. Let's suppose you can go and do it. How will they typically look like? Okay, the heat transfer coefficients as a function of x. Well, what is going to happen is here at the leading edge of the plate, at the leading edge, the temperature gradients is going to be the largest. Okay, dt dy is going to be the largest there. Okay, do you agree? Okay, the largest gradients is going to be at the leading edge. So the heat transfer coefficient there is going to be quite high. Okay, but now remember, heat is being transferred to the fluid. Okay. So what happens to its temperature? Its temperature is changing, and the result is that this temperature gradient is actually changing as you go downstream the plate. So because this temperature now here is higher than there, the gradient is going to be different, and the result would typically be that the heat transfer coefficients, if you go and measure it at different positions, is going to do something like that. Okay, so that would be the heat transfer coefficient at point 1, that would be at point 2, point 3, and at point 4. So in general, the heat transfer coefficients are not the same. Okay. At a stage, they will get to the point where the flow is so-called fully developed, and we will get to that later on, and then they will be the same. But in general, the heat transfer coefficients will not be the same. So as engineers, if we are interested in a specific body, whatever, and we do have data like that, well, we're going to look at it like this and say, well, that is sort of the average, okay, and we would like the average heat transfer coefficient. So in many cases, we would like the average, okay. But to get the average, obviously, we need to understand what is happening on the inside of it. Now, another very important group that we use with convection heat transfer is the Nusselt number. Okay, so the Nusselt number by definition is equal to the heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity. Just want to clean the board on this side. Okay. So, the Nusselt number is a non-dimensional variable, and it is equal to the heat transfer coefficient multiplied by a characteristic length divided by the thermal conductivity. Again, this thing of the characteristic length. You remember with the Biot number, there was also a characteristic length. So if you look at fluid mechanics and heat transfer in general, ladies and gentlemen, listen, okay. There are many variables. There's the Reynolds number, there is the Nusselt number, and there are going to be many more. All of them are usually based on a characteristic length. And you need to know what it is, especially when the experiments were conducted. Because if you use another one, you're not going to get the right values. So it is very, very important, and it's a trap in general. So always be very, very careful when you calculate the Reynolds number or the Nusselt number, that you know what characteristic lengths were used when the experiments were done, or when the correlation that you're going to use was developed. Okay. Now I just want to give you a very simple example. Let's suppose we have a flat plate, okay, and the temperature on the outside is 100 degrees Celsius. The heat transfer coefficient is equal to 100 watts per square meter degree Celsius. Okay, and this is a copper plate, okay, and K for copper is equal to 400 watts per meter Kelvin or degree Celsius. And this characteristic length, LC, the characteristic length is I think 8. Okay, 8. Okay. Okay, so calculate the Nusselt number for me. Simple, isn't it? Okay, Nusselt number is equal to the heat transfer coefficient multiplied by the characteristic length divided by K. Heat transfer coefficient is 100. The characteristic length is 8 and K is 400. So the Nusselt number is equal to 2. You happy with that? Who said no? Why?
Because that's not the characteristic length that you used. It's not just the length of the plate. It's area divided by volume divided by area.
Well, no, I can say the Nusselt number based on the length of 8 meters. So as long as I do that, that's fine. Okay, so I actually, yes, if I say a Nusselt number, I should say on what length it has been based, and in this case, the length of 8 meters. Any other objections? No. No. What's wrong? The what?
The K value should be for the medium and not for the material.
It's such a simple thing, but many of you are going to make this mistake. So, it should be the K of the fluid. Okay, so you should have asked me, but you didn't give us the K of the air. Okay, and the K of the air typically would be equal to 0.03 watts per meter Kelvin. Okay, and look at the difference it's obviously going to make. So now the Nusselt number is equal to the heat transfer coefficient multiplied by the characteristic length divided by K. It's equal to 100 multiplied by 8 divided by 0.03, and now it is something like 27,000 watts per square meter degrees Celsius. Okay, so be careful for that, okay? That you do not make that mistake when you calculate the Nusselt number. The Nusselt number is an indication of the heat transfer in the fluid. And I'm going to explain it to you in a little bit more detail, specifically what the Nusselt number means. So, the physical significance of the Nusselt number. Let's just go and look at what does the Nusselt number mean. And we take some fluid, okay? And it's a fluid layer, typically. Okay, a fluid layer. Okay, and what we now have is, we say that let's consider that temperature there as T2 and that one T1. And the difference between the two fluid layers is L. Okay, now the two fluid layers can be very, very close to each other. It's not that we're talking of meters now. So, what we can say is if the fluid is in motion, therefore it is convection, okay, then the convection heat transfer would be equal to the heat transfer coefficient multiplied by delta T. And delta T would be equal to T2 minus T1. Okay. If the fluid is stationary, okay. So firstly, if it's in motion, then if it's stationary, then it would be conduction. And if it's conduction, then we can say that the heat transfer rate of conduction is equal to K multiplied by delta T divided by L. Okay. Let's take the ratio of the two. So the ratio of the convection divided by conduction. The ratio of convection to conduction, and now we have the heat transfer coefficient multiplied by delta T divided by K delta T divided by L. We see that the delta P's disappear, and now we end up with HL divided by K, or the Nusselt number. So now, except now for the fact that this is the ratio of convection to conduction, what does it really mean? It represents, what does it represent? It represents the enhancement in heat transfer. The enhancement. It represents by how many times the heat transfer will be increased. So, if the Nusselt number is equal to 1, okay, if that ratio is equal to 1, then we know it is conduction heat transfer only. Okay. If the Nusselt number is equal to 3, then it means the bulk fluid motion. The bulk fluid motion, okay, increased the heat transfer rate with 300%. The heat transfer rate would be increased by 3 times. That is what the Nusselt number means. What does it mean if the Nusselt number is smaller than 1? If it's 1, it's conduction. If it's more than 1, it is by how much it has been enhanced. That is what the Nusselt number actually means. If it's smaller than 1, it means you've made a mistake. Okay. Can't be. It's a fundamental error. Okay, fundamental error. And it can happen very easily. Some of these equations you will see are very, very long. And all of us make mistakes when you do the calculations. So if you get a Nusselt number smaller than 1, you must know it can't be. It's a fundamental error I'm making. Okay. Any questions on convection heat transfer and the Nusselt number? Nothing. Yep, question.
I just want to find out the unit you wrote there with the Nusselt number. That can't be correct.
It can't be?
Correct.
Should it be meter squared?
At which one? Oh my goodness, I'm sorry. Yeah, it's a non-dimensionalized thing. Sorry. Sorry, yeah. Sorry, I got it. Yeah, okay. Nusselt number is a non-dimensionalized value. So in this case, thank you very much. Okay, that's a good example. Okay, a good example. So it means this Nusselt number of 27,000 means that the bulk fluid motion increased the heat transfer rate by 27,000 times. Okay. If there was no bulk fluid motion and no gravity and only conduction, then the heat transfer rate would be 27,000 times lower. So that would be what the bulk fluid motion will cause in this case. All right. Right, we are not finished yet, unfortunately. Paragraph 6.2 is about the classification of fluid flow. Classification of fluid flow. Now in this paragraph, paragraph 6.2, there are work that you need to read through very carefully, and it is important, okay? But it is work that you've already done, but we are going to use it. So firstly, the classification of fluid flow is a very short summary of what do we mean with viscous versus inviscous flow, internal versus external, compressible versus incompressible, laminar versus turbulent, natural or forced flow, and steady versus unsteady flow, and then one-dimensional, two-dimensional, and three-dimensional flow. Are you all familiar with this? Do you know it? Easy. Okay. It takes a long time, before you get used to it, and in that regard, there's one flow regime that I specifically would like to discuss with you, because I know so many of you have problems with it. And the problem I'm going to select, or the example I'm going to select in doing it, is a gas turbine on an Airbus. Okay? So let's suppose that is the Airbus wing. I'm not going to try to draw the wing. Okay. And there's a gas turbine engine. And the gas turbine engine, schematically, if I can show it like that. Okay. And the Airbus is moving at a Mach number of 0.2. Okay, so the Airbus is moving at a Mach number of 0.2. So, and you're going to do this in the next semester, when you're going to look at gas turbines. But with a gas turbine, the first thing that's going to happen is there's going to be blades there, okay, and they're going to direct the flow. And then just after the blades, there's going to be another set of blades, and they are rotating, okay, at a very, very high speed. Okay. And then again, after that, there are some blades again, which are stationary. So they direct the fluid again for the next set of blades. Okay, and this goes on quite a few times. Okay. The purpose is to compress the flow. So that is called the compressor. So the compressor, the combustion chamber, and the turbine. Right, so in the combustion chamber, gasoline is being added. There's a big fire, and as you can think, things expand, and the pressure is going to increase. So there we have a high pressure and high temperature. Now it is going to be expanded through the turbine. Again, there will be some blades there that will direct the flow to the blades of the turbine that rotates, and again another set of blades and another set of blades, etc. Okay, so that is a gas turbine. Compressor, combustion chamber, and a turbine. Now let's look at the density typically through this. What will happen with the density? So if this is now the air coming in, going through the gas turbine, what will happen with it? Right, what will happen with it is that firstly, in this region here, it would be the outside density. Okay, if it's at 10,000 meters, then I think it's something like, I don't know, 0.1 or 0.2, something like that, very low density. But the flow there would be incompressible. Okay. Two reasons. Firstly, the density doesn't change, it's a constant. The Mach number is smaller than 0.3. Okay, so it is incompressible. Then things are going to start changing through the compressor. The first set of blades is not going to do much, but then after that, the density is going to increase because the pressure, the air is being compressed. That's the function of the compressor, is to compress it. Okay, then in the combustion chamber, it's going to increase more, and then it has to expand again. And in the expansion process, it goes through the turbine, through all the different stages, and then it will go out like that again. So There it's incompressible, and there it is incompressible. Okay. In this region here, it is compressible. For obvious reasons, we can see the density is changing as a function of position. Do you agree? Okay, now let's look at how the density changes as a function of time. Let's suppose we do a measuring, we measure the density at position 1 there, okay, and position 2 and position 3. So we measure the density. So the density as a function of time, take note, now it is a function of time, and it is in a specific position in the field. Okay. So what happens with the density at point 1? Well, not much. It's going to be quite constant. Okay. What will happen with the density at point 2? It will be higher than at 1, but it's not really going to change. Okay. In position 3 is about the same, typically something like that. Okay, and that would be the inlet of the compressor, so our gas turbine would be operating in that region there. Okay. Oh, no, sorry, I shouldn't actually do that. Yeah, forget about that, sorry. Because this is now a function of time. Okay. Okay, so this flow is steady. So it's steady flow. Okay. So the flow would be steady and incompressible there. And at position 2 and 3, it would be steady and compressible. You agree? So at 1, it is steady and incompressible. At position 2, it would be steady and compressible. Right. Now what happens if we get a bird strike? Okay. Now we have a poor chicken going through the gas turbine. Okay. So by the way, how do they test these things? If they test it on ground, they use frozen turkeys to throw through the engine. Okay, I'm serious. Frozen turkeys are being used. Okay. Okay, so what is now going to happen with the density as a function of time? Okay. Okay, at position 1, if you're measuring there and you don't see the bird, then the density is going to be constant, and then suddenly the bird is going to be there, and then that is going to happen, okay? So steady, and then suddenly unsteady, and then steady again. At position 2, just a fraction of a second later, it would be like that, and in position 3, something like that. So that is the unsteady flow behavior, okay? Obviously, the unsteady flow behavior we will also have when the engine is being put on and off, or when the throttle is being changed, more fuel or less fuel, then we have an unsteady behavior. So make sure that you really understand the differences between steady flow, unsteady, compressible, incompressible. Okay? Thank you very much.